we are here with Professor David Bruhn. So he's professor for geothermal engineering at the Department of Geoscience and Engineering in the section Petroleum Engineering. And at the same time, he's also senior scientist at the GFZ Potsdam in the geoenergy section. So he's doing twist between Germany and Netherlands. And his other task is scientific secretary of the joint program of geothermal energy at the ERA, so European Energy Research Alliance, for those who didn't know, involving more than 30 academics from 20 countries. Is part of the steering committee member and vice president of European Technology and Innovation Platform for deep geothermal energy. He was associate director of the geothermics review and member of the deep geothermal working group on the implementation of the set plan. Among his research activities, the development of deep geothermal resources for direct use, either in hot sedimentary aquifers, but also in enhanced geothermal systems. Also involved in the exploration, methodology and how to find the good resources, and also in the geological storage by geothermal heat storage with high temperature. So thank you very much, David, for your presence in our geothermal winter school, and your title is still what was planned, determining the key factors and suitable measures for successful enhanced geothermal system developments. David, the floor is yours. Thank you.
Okay, thank you, Xavier. I'll start sharing my screen, right?
Yeah.
And then, okay.
Now, yeah, it's good.
Okay.
We have it.
So the key, it's quite an ambitious title, determining key parameters and suitable measures for successful EGS developments. So the idea of this was to actually try and determine what is the actual difference of an EGS development from a let's say conventional geothermal, because if we look at this, 2008 there was this evaluation of enhanced geothermal systems technology by the Department of Energy in the US. That was after all the first tests in Fenton Hill and Rosemanowes and Soultz and in Japan had been done, and so that's when they published this evaluation. And in this evaluation, they say the key components or the site properties that should be known for successful creation of the reservoir include temperature gradient, stress field lithology, stratigraphy, structure faulting, in situ fluids and geochemistry, geologic history, seismic activity, proximity to transmission, land availability, demographics, all these things. And when I look at this, I say this is not EGS specific. This is generally geothermal. I mean, lithology, stratigraphy, in situ fluids, all these things. They're also extremely important for conventional hydrothermal resources. So what is it that really makes it an EGS different from a normal hydrothermal or conventional hydrothermal? And I thought that I would go back and review the old, let's say, these historic projects that actually led to what we know today and what we are doing today, like the lessons learned from these very old experiments that were done in let's say EGS history. So the first one ever, or the one at least we consider as the mother of all EGS projects, is at Fenton Hill in New Mexico. That was initiated by Los Alamos National Lab, and they called it the first hot dry rock project. And the reason for that is that they were really targeting at hot dry rock. So it was really dry. And so here you see Los Alamos National Lab. So somewhere somewhere here on the right must be Santa Fe. And Fenton Hill is at the edge of this Valles Caldera, where you actually, and in these mountains here, you actually do have like hot springs. So there is geothermal activity, but they deliberately targeted an isolated granite body that was very hot, and they thought it would be like a nice little, a nice place to test the technology. And the initial idea was to actually do a nuclear explosion down there to stimulate the granite, and they decided maybe that's not such a great idea, and then let's go for hydraulic fracturing. So the hope was, you know, that this granite was completely, let's say, isolated body. It was not connected to anything else, so they could create a reservoir and design it themselves. So that's completely enclosed. And that is what the original idea was. You know, you basically you have a couple of deep wells, one deep, one very deep, and you create a crack in the very deep one, like and the crack will of course follow sigma 1. Yeah, this is what we learned, and sigma 1 at these great depths will be the vertical stress. So, and then you just connect the deep and the not so deep well with this one big crack, and then you have your fracture zone that will result in your nice artificial reservoir. So, well, you know, this is just a photo of the test site that I managed to find in the internet. You know, what they actually found out is, because they did a lot of very advanced and nice concepts that we still use today. It's like, for example, they did very careful and very good seismic monitoring, because they realized that, you know, the opening of the fractures would create seismic noise, and that by recording that, they could actually see how the fracture would develop. Now, what you can see here is, you know, there is the injection well and the production well, you know, top view. And what you can see is that, you know, the seismic noise is all over the place. And it's definitely not just from a vertical fracture. And that is exactly what they realized. They didn't manage to connect the two wells. So they basically had to drill or deepen the well or drill another well and manage to drill through the seismic cloud. And then when they started to circulate fluid, they realized that a lot of the fluid didn't actually arrive at the other well, and instead they had seismicity further to the south, and etc. So that the reservoirs seemed to grow with time, but it wasn't accessible by the wells they had drilled. So what they actually learned in this whole procedure is that, you know, it was nice that you could actually drill deep wells in these very hard and abrasive rocks. I mean, they wanted to drill deep because they also went to temperatures like above 300 degrees. So everything was actually looked kind of nice. So what they also realized that you can stimulate this low permeability crystalline rock and have hydraulically conductive fractures. You can create permanently open networks of fractures in large enough volumes to sustain energy extraction, which means more than 1 cubic kilometer of stimulated rock. You can circulate for extended periods of time, even though they had to see that also they had a temperature decline after a little while. But what they realized is that creating a connection between the wells was difficult. So it was easier to actually drill one well, stimulate, and then drill into the fractured volume. And what they also realized is that the fracture pattern that they actually observed did not match what they predicted. And also what they realized is that to actually keep the fractures open, they needed to inject at relatively high pressures, so they could maintain high enough flow rates, but then the reservoir would grow and the water would be lost. towards the sides where it wasn't accessible for the wells anymore. And if they reduced the injection pressures to reduce the water loss, which was possible, but then the flow rates were really low. So the high pressures needed to keep the joints open caused operational problems and required substantial amounts of power. So energetically, it wasn't, let's say, a success, but in general, it was a success because they managed to show that it works. They can actually create even large enough volumes, etc. But there were all sorts of things that didn't work so well, lessons learned. And eventually the whole thing was abandoned when it was clear that it would require substantial more investment to run. Then there was a follow-up that was also inspired by the Fenton Hill project. It was in Rosemanowes in the UK. They started a few years later, not much later actually. And that's, you probably heard a lot about this site already during the last few days, because that's the site also where the United Downs project is. It's Rosemanowes, very close. And they said, okay, we understood a little better. Now we will do something different. And also one thing they said from the start is, okay, this is an interesting location, but all we want to do is try and test if this works. We are not going to generate electricity here or anything, because going to these high temperatures also required downhole tools and instruments that didn't exist at the time for these high temperatures, right? So they said, okay, we'll stay below 100 degrees C, so we can make sure we can still observe things that are happening there. So, and the concept they had was that they also wanted to drill 2 wells and then stimulate them, and they were hoping that they now realized that they would probably not just trigger or generate one big fracture, but they still wanted to connect those two wells. And what they thought, you know, that they would drill these 2 wells above each other, and the fracture cloud would actually go to the top, you know, from the bottom well. And what happened is that it actually went all the way to the bottom, that it actually went downwards. And so they ended up drilling another well, a 3rd well, to access this one. Okay, so that's what they realized. Okay, we drill into the cloud, and then they managed to get a relatively good connection, stimulate it again, and they had really good flow. But after a while, they realized that they were producing already the cold injected water, and so temperatures were declining rather rapidly. So they had probably stimulated too much, and managed to create a thermal shortcut. So the lessons learned from Rosemanowes were that the fractures created by hydraulic stimulation, they are not formed through tension, because that's what they realized. They didn't really manage to open those tensile fractures, but they actually created shearing on pre-existing joints and fractures. That is something they realized at the time. The stress fields in crystalline rocks, they are always anisotropic, so it's really difficult to predict exactly how they open, but also natural fractures fail in shear. And then once they're sheared, they self-prop and stay open. So this is what was realized at Rosemanowes. It is possible to stimulate natural fractures and improve permeability and create a connected volume of hot rock. So that's this fundamental, let's say, difference in thinking. You know, we stimulate natural fractures and improve their permeability. A prediction of the direction of fracture growth is difficult in the absence of precise downhole data. So if we don't know exactly what the stress is, even with near wellbore data from image logs, the fractures may not grow exactly as predicted. So that's why it's better to create the reservoir first and then drill into it. But probably the most important single lesson from this experiment was that the hydrofracturing of artificial fractures is almost irrelevant. So you do create maybe small tensile fractures, but the natural fracture system dominates everything. That's a key lesson to remember. And overstimulating pre-existing fractures can result in a more direct connection. That's what they observed by having the short circuit through the reservoir. So you don't want to overstimulate, right? So, okay, then there were 2 follow-up projects also in Japan. I only put 1 dot because they're very close to each other. Ogachi and Hijori, at least at this scale of the map. They are relatively close to each other. And what the Japanese, they were actually also involved in Fenton Hill at the time. You know, Fenton Hill was initiated by Los Alamos, but it was an international cooperation, and including Japanese involvement. So what they wanted to do in Ogachi and in Hijori, both they're kind of also near volcanic, in volcanic regions, of course. They wanted to drill also in granodiorite and have the wells very close to each other, because they thought, okay, let's test this. We really want to make sure that we managed to have a communicating system. It was a real research approach. And basically, they had the same thing, you know, that the reservoir continued to grow during the circulation test. This is also what they observed at Fenton Hill. And they also realized that they could have short circuiting like in Rosemanowes. But what they really found is that, you know, that the acoustic emissions, they indicated that the stimulated fractures actually change their orientation with depth and away from the well. So what they saw is that there wasn't obviously one stress direction, that the stress field changed. And the same, so in Hijori, it was away from the well, and in Ogachi, it was, if you actually went further down, they didn't manage to connect the fracture set that was further up. Sorry, I have maybe to go back. You know, they had the upper fracture and the lower fracture zone here, and they didn't manage to connect this so well, because they realized that the orientation of the fractures in the lower fracture zone were not the same. So it was not so simple to connect the two. So there was a change in direction of stress. So, and you know, with all these lessons learned, also Soultz, I mean, some of the developments in Soultz were parallel, because they started already in 1987. But you've probably heard a lot about Soultz also in the last few days, and so I'm not going to tell you what they all did. But basically, Soultz profited quite a bit from the experience. Also, the crew at Soultz, many of them were involved in Rosemanowes, for example, at the beginning. And the setting was also a bit different. You know, when you see, in Japan, for example, also in Fenton Hill, they were looking at these volcanic caldera regions, where you probably have a distinct stress field around the caldera. While in Soultz, they are in this extensional setting. So you have the Rheingraben setting, or it's so there is this, let's say, a chance that fractures actually stay open more naturally in an extensional system. And so that is quite a favorable situation. So what they did, as you know, they drilled a total of 4 wells. So I have a multi-well system at almost 5,000 meter depth with temperatures around 180 or a little more. And they stimulated successfully, had several tests, and now the whole thing is running, right? And what they also did, I really like this, the monitoring of the fracture growth just shows how the stimulation works, that it was successful. You see the seismic cloud. And yeah, well, I know this has been shown a lot about Soultz, and I like to show it because I think it's really beautiful. Anyway, so the thing about Soultz is that, you know, after so many years of research, they actually went into an operation, which is now commercial operation. They spent a lot of money, research money that came partially from the EU, partially from France, partially from Germany. And they profited a lot from previous knowledge, also from Rosemanowes. And that was a fantastic, or still is, I mean, it's still a fantastic operation that continues to generate or inspire scientific research, more than 40 PhD theses, etc. And now follow-up projects were generated there because it's successful. Now, what we learned now also in Soultz is, in Soultz, they also started the whole project as a hot dry rock project, right? And what they realized is that the rock wasn't properly dry, right? They found fractures that showed, let's say, traces of, or how do you say, that showed proof that there was fluid circulation in these fractures. So that's why we also the definition of the enhanced geothermal systems came because people realized is, okay, our chance is better to enhance an existing fracture network than to create one in a hot dry rock. And if we enhance an existing geothermal system, then we have a much better chance of success. So we are no longer targeting really dry rocks. We are maybe targeting unproductive systems, and that's why enhancing this is an enhanced geothermal system. So the way this works, we have these extensional fractures when we increase pore pressure. That's the ones that follow sigma max, right? And if the pore pressure is decreased, then they close again. So you have to keep the pore pressure high. And if we want to keep them open, we have to put proppants in them, right? So then they stay open. But what we actually primarily go for is those shear fractures, because when we increase the pore pressure, we have displacement along the shears, and then when they close again, there is the self-propping effect, and then we still have a permeable structure. So I didn't manage to follow previous lectures, but I presume you have seen something like this many times already. So we have this whole, let's say, we have everything from not permeable at all to very highly permeable hydrothermal system, everything in between. And when sometimes, these impermeable systems where they are dominated by the heat from the rocks, they are called petrothermal systems. And if they're dominated by really hot water systems, they're hydrothermal systems. But you have any transition in between, and whenever you need to stimulate and treat them, you can talk about enhanced geothermal systems, right? Now, one thing that was really important to learn, we come back now, is like one of the key components of enhanced geothermal systems is really fractures, right? And this is one difference to conventional systems. They can have fractures, but they don't have to have fractures. But in enhanced geothermal systems, we really want the fractures, right? So I would say that's one of the key components is fractures, existing fractures. And we've seen, that fractures that you stimulate from your well, if you want to create new fractures, they follow sigma 1. But as soon as they are that they reach the natural fracture network, then they follow existing fractures like here. Yeah. Now the question is, of course, how do we find the fractures, and how do we determine what the fractures are? And there are ways to do this downhole. So we need to drill first, right? So all these logs. But if we don't want to do it like this, then we maybe need to map them first, right? And so what I thought is, I will show you briefly how this can be done with the scanline method. Maybe several of you have done this before. It's not something that I came up with or anything. So people have done this before. Something you can do if you want to map fractures, for example, in an analog outcrop that represents your reservoir depth. And so this is examples that I show you are from the island of Elba, which is considered an analog outcrop for Ladarello. And so I got these slides from Martina Zucchi, is a former PhD student at Bari University. She was also the host of the EGPD a few years ago. And she mapped all these fractures with the scanline method. And the way this is done is that you actually don't map all the outcrops from A to Z, but you actually take like statistically significant examples. So you take, like, you have your let's say 20-meter long profile, and then you take a square of 40 centimeters each here every 2 meters or every meter, right? And then you map every fracture in this square. And that's, so I'll take you down there, right? We take the road down here, then we are at the outcrop, Top Pineti Beach. And then this is what you do basically, right? So we map all the existing fractures, and what we measure is the width and the length of the fractures we can see. Okay. And with this equation, we can then calculate permeability. And the reason why this is, let's say, possible, I mean, this is based on a parallel plate model that you can calculate permeability from this, and I have put the sources here. But the key is, because, you know, these are not fractures, these are not open fractures, these are all closed fractures that are, and they're closed because they're mineralized. That shows, they all show traces of fluids, of fossil fluids, I have to say. So it's a fossil geothermal system. That's why we can say they are the way they are also at depth. You know, if we have open fractures, we don't know if they would look like this also at depth. But these are closed fractures or mineralized fractures. So we can say these are an exact representation of what they looked like at depth when the fluid was still percolating through them. So I invite you to come with me to Topinetti. There's Martina. She's just taking a measurement here in one of the squares. I sent you handouts, a couple of handouts, and those contain the equation that I just showed, and they show a figure and a picture, I mean, of the outcrop, and it includes an Excel table where you can put like numbers for the fractures you measure. Like we go through this, you know, these are just examples from the outcrop. Here, you know, you have this square, you have then you see the fractures, and then you can measure the length and the width. And that's the one that I want you to look at, and I will also put it on my screen. So you can do this either on your screen with a ruler or whatever, or you take it on a printout of the handout that I provided. And then you join my group. This is a group from TUDelft. They are trying to evaluate what they were measuring there together with our friends from Italy. And yeah, please come and join them. And so what I will do now, I will stop sharing for a moment. And then I will share the actual image. Hang on, where is it? It doesn't want to let me do that. Hey, too bad. So yeah, please take the handout, and I try and find it for the time being.
Okay, as I mentioned just early in the before you started, David, all people, you should have received the handout that David is speaking about, and you could print it or put it in your screen for a
Can you see it now? In case you don't have it, I just try and put it on the screen. So yeah. Is it visible now? For those who don't have the handout.
We see photos.
Oh, just photos. You don't see the photo. Okay. Because I'm just trying to share the one photo with you. Okay. Then okay.
I think we see your desktop.
Yeah, I know. And what I'm trying to do is open the picture. Actually, and it doesn't let me show you the picture. You know, that's what is annoying. I go in photos. You should see this. Do you see it now?
This is great.
Yes, it's good.
Okay, and so now I give you, let's say, oh God, it's already past. Okay, I just give you, let's say, 5-6 minutes, and you don't have to measure all these fractures. Just choose a couple of fractures and put them in the Excel table. So what you need to measure is the length and the width. Okay, and the width is ideally because the width is something that is not, let's say, a single number. So you take the maximum and the minimum width. And you know, I know this is not going to be very precise, but the point is, you know, we'll try and do it here. And ideally, you do this for the entire square, and then you move on and do it for the next square. And then you can calculate an average permeability of your section, right? So this is what we are going to do right now. Then we collect the numbers. You calculate the permeability with the equation. If you don't have the handout, I will put the equation. And so at, yeah, in 5 minutes, I will stop you. And then we collect your numbers, right? So there is an answer, a question. Maybe I should say
yes,
this, the answer.
There is I think this is a question for the.
Yeah, this is a question
for the exercise actually. Yes.
Exactly.
Yeah. Can the estimate permeability of the outcrops represent the reservoir fracture?
Yeah, that is absolutely correct. I mean, you can measure the filling material is, as I say, you know, this is a fossil fluid. This is basically precipitated from the fossil fluid. So you can measure that as the content, like this is the fracture content, so the fluid. So you measure from one side of the wall of the fracture wall to the other. Okay, consider this as the fluid, as the open part of the fracture. I know that you got extremely little time for this, and I didn't want to have an exhaustive, let's say, evaluation of this one outcrop from you. I just wanted to give you a very, very small piece of a little flavor of how this can be done, because I will continue and show you what else can be done with this and why I think it's a really nice method to use. But first of all, I stop sharing, right? And then maybe we can go to the okay, what happens if the fracture is longer than the square? You just take 40 centimeters, because that's the length of the square. I know in reality this will be different. Okay, if you don't limit it to the square, you can say the fracture is 20 meters long or something like that. But for the time being, you just count it as 40 centimeters. Okay. So what I want to do now is we put something in our Excel sheet, right? Now, where is it? And you give me your numbers and we put them in, right? So I left five fractures in there as an example. And now you have to be courageous and tell me your numbers, right? Speak, that's what I mean. You give me a few numbers, we put them in there, and then we can calculate maybe the permeability.
Maybe yeah, I can give them right to talk. Would be easier. Okay.
Otherwise, yeah.
Okay. I mean, everyone can speak.
Yeah. So I see there are 71 people, so I expect at least 71 fractures. Oh well, that's too many. But a few, come on.
0.001 to 1 millimeter.
Okay, good.
21 centimeters for the
length.
For the same.
Oh, for the length, yeah.
For the length.
Good. That 0.4 we take here as well. You know, that's the connection factor that we have to take. That shows how well the fractures are connected. That can be anywhere between 0 and 1. So we take just an okay.
And the same for the width, please. And 41 40
Here.
centimeters. Yes.
And they're 40. Okay.
Yes, please.
Oh, hi. Oh, that's so there. It's also
Yes,
between.
the same 1 millimeter. Yes.
All right. Good. Excellent. Any other numbers?
Okay, I think Ezigul tried to. Okay, Gemma Mijana said B minimum is 0.0005. Can you hear me, David?
Yeah, I can hear you. Hang on a second. I need to go back. I was just.
Yeah.
Okay, so where am I? This is the one. Okay, 0.005. Oops.
Yeah.
What did I do? Yeah. 0.005. Oh, 005. Okay, one more.
Then 0.001, 0.15.
Excellent. And 0.4. And then
someone else.
One more.
Another one. Same 0005. Like this, yes. And then 002.
Oh, okay.
And 01.
Oops.
Eduardo wants to give his value. Come on, Eduardo.
One more, huh?
Hi. Yes. I had 0005, so 0.5 millimeters as well.
Okay, same here. Okay.
Yeah, same as there. I found a pretty big one, but 0.008. So maybe it's bigger than. Maybe my measurement techniques are a bit off, but
That's fine.
and 0.3 length.
So pretty long. Cool.
Yeah. And this connectivity, I didn't really understand. But
I will explain it in a second. So the connectivity is simply a factor that we apply because it basically it you know, as I said, it can be anything between 0 and 1. So 0 is they're not connected at all. There's no communication. 1 is that they're 100% connected. So we take something in between. It's not that important because if you look at the equation, and maybe I can go back to the equation in a second, you can see that it only comes in with a 10 to the minus 6 factor, right? So,
yeah.
so maybe you double or triple your permeability, but you don't change it by an order of magnitude if you change your connectivity. Okay, so that's the key. So all right, and
then you have few values from Armand in the Q&A, and there are a couple of others from Marc and Jérôme, if you want.
No, I don't want to anymore.
It's okay.
I have to stop because otherwise, you know, it's good that you have done all this. This is great. Now I need to stop sharing and need to calculate the permeabilities. But unfortunately, this was not very practical, my idea. So, but what happens? Oh, hang on. Okay. So the permeabilities we get are all in the range of somewhere 10 to the minus 15 to 10 to the minus 18 square meters, right? That's the result of this calculation, which means this is practically this is this is in the range of, let's say, good geothermal reservoirs. Like this is also what people calculate for the depth of Laterello, by the way. And I want to go back and show you the equation so we can actually go back to the theory and then we can continue. If you remember what I showed here, this is the equation, right? So this is your width and your length, and this is the connection factor. And that's on the handout I provided. This is actually that's where you have this equation. So this is how you can, this is a simplified way to calculate the permeability. It's a back of the envelope calculation, but gives you a pretty nice, let's say, yeah, ballpark number to see if you know, this kind of fracture network would result in a good permeable network. Now we go back to what else can be done with this method and why I'm showing you this, okay? So I had a PhD student who finished last year, Baptiste Lepillier, who actually did this in Mexico. You know, he went to an analog outcrop that's here on the right in a place called Las Minas. It's an old quarry, and that's the analog for these sites here at Los Humeros and Acoculco. And Acoculco is a dry site where they wanted to do an EGS project. And all we had was some limited logs and, well, this beautiful analog outcrop. And so this is what Acoculco looks like. And a lot of mapping actually showed that, you know, this is where the borehole is, this is where the red arrow is. And that there is actually a major fault zone here. And so the idea is that this well actually went into the magmatic intrusion, which is like a granodiorite. Then you have this marble and limestone succession and the contact metamorphism there. So you have a skarn and you have volcanoes, volcanic succession above. So this is what it looks like. And this is exactly the sequence you have at Las Minas. At Las Minas, the whole thing is uplifted, has been is exposed. And so Baptiste could actually go there and map this comprehensively. And so you can see all these different generation of fractures. And, you know, this is where you see he was not alone. There were other people. There was a huge project, the GEMX project with many people involved. So they were all working along this scan line here, right? So a 50-meter outcrop here. And this is, he actually got 7 generations of different fracture sets. So, and what he did along the scan line, he actually didn't just measure the width and the length, he also measured the orientation and he measured the entire length, right? So the 20-meter length. And he also didn't do the boxes. He actually went along the entire thing, right? So that was quite a long way. But the reason why he wanted to do this is because he wanted to compute district fracture networks from them. And together with another postdoc at TUDelft, you know, they developed this method to develop a distributed discrete fracture network from these data. And this then, you know, at the end served as the basis for modeling, you know, how the fractures would develop once you inject fluid. So that's why I think, you know, the scanline is a good way to look at fractures. But the other thing is, you know, now we need to also understand how the fractures form, and because this is what we and how they behave when we inject. So what we know is that fractures they form as and react to stress and as a result of stress, right? So this is a beautiful experimental example where you can see, you know, there was a uniaxial compression, and what you had is you have this sigma 1 is here. You can see that there is this fracture forming, so a tensile fracture, but you also have shear fractures forming, right? And so this is so they have a certain orientation with respect to the different stresses, right? Maybe all of you know this theory, Andersonian. Here that you have in an extensional regime where you have more normal faulting, and in a compressional regime where you have reverse faulting. So in this case, the maximum horizontal stress is larger than the vertical stress. Here, the vertical stress is larger than the horizontal stresses. And you can have strike slip faulting, of course, if one of the horizontal stresses is larger than the vertical stress. So whichever fracture is activated depends on the orientation of stress. Okay, so what I wanted to show here, and this is important, is that when we are near the wellbore, locally, the fracture will follow the fabric, pre-existing fractures. I mean, you can have like a little bit of an hydraulic fracture opening that follows a tensile stress, because there is no fracture very close to the wellbore, not a suitable fracture, but then it will follow the existing fracture network. But in the overall direction, so the large scale direction will follow the stress field. Okay? So we have the combination of stress and fractures, very important. So how do we know the stress? That's one of the questions, how do we determine the stress? Maybe you all know the world stress map, and how the stresses are determined in the world stress map is very nicely explained. There are very many different methods, from focal mechanisms or from overcoring, from borehole breakouts. I'm not going to explain that here, but there are many ways to determine stresses or to look them up. But very often we don't have the stresses, right? And it can be confusing, because if you look at this here, and if you remember the story I told you about the Japanese wells, you can have stress fields that is different at different levels, and you have this kind of confusing situation like here, where you have stresses in all sorts of directions and you don't know what that's supposed to mean. And if you look at the interpretation here, you can see you have a mechanical decoupling of a salt pillow. So the top layers, that the dominant horizontal stress is this, and at the bottom layers below the salt pillow, the dominant horizontal stresses are this. So this can happen, and this is very difficult to know unless you have actually looked at the borehole data. But there's something to realize, that stress, even though the overall stress field in your world stress map may be clear, locally it can be very different. Like if you have a salt dome, or if you have these volcanic calderas that I was showing before, like for Fenton Hill, for Ogachi and Hijori, they can locally the stress field can really deviate from the overall regional stress field. So around a salt dome, you will have fracture openings in all these directions, because that's how the salt dome changes the local stress field. But as you go further away, they're more likely to follow the regional stress field again. So I guess I'm really running out of time, and I apologize for that. What I wanted to say is, like, I skip all this. There are all these things that here this shows that the stress field will actually is dependent on the lithology, right? It's that you have your sequence of sandstones, mudstones, salt, etc. And you can see that the stress, the maximum stress or the minimum stress can actually be, can be very different from layer to layer. And this is important to know. So you can have a stress gradient plot where you can see this, that there's a dependence on the mechanics of the rocks. Now, what I wanted to do in the other exercise is let you calculate the actual fracture pressure that we need to frac. I'll stop that now. That would have been the equation. Because what's important is also that we know that once we actually introduce a fluid pressure, then this is what we want. We want the fluid pressure to exceed the minimum horizontal pressure to get a fracture, for a fracture to open. But what can happen is, depending on your stress field, the fracture can have different shapes, and depending on your mechanical properties, you have different properties in your rocks, your fractures can have completely different dimensions and different shapes. And this is really important to know your stress field when you design your fracture experiment or your fracture thing. So I'll stop this here. Just show you that, it's very important to also know the rock properties. Your fracture can be blunted because your rock is very permeable above. You're fracturing here. The rock above is permeable, so it will completely blunt. The fracture will not follow, because the pore pressure will completely decay in that region. It will not actually expand that way. So it's important to know the rock properties when you want to fracture. And with that, you know, also with more competent or harder rocks, you know, you will have a much thinner fracture than in softer rocks, etc. You know. So with this, I would like to finish and apologize for losing you in the way. And the key, what I'm trying to say is, okay, the key for me for EGS is not all these, all the things that are true. You know, you need the fluid chemistry, you need your stratigraphy, you need your geological setting, and all these things, they're important. But the key for EGS are these three things. You need to know your rock properties. You need to have fracture networks, and you need to know the stress. And this is how you can finally come to a successful EGS design. Yeah, these are the key, in my opinion, these are the key parameters or the key components of an EGS design. These are things that you don't necessarily have to know for conventional geothermal systems, right? And with this, you know, that's the approach that Baptiste chose also for Acoculco. That's why I took this from his thesis. This is the way what he followed. You know, he did mechanical measurements. He did develop the discrete fracture network and developed a fracture propagation model for this. And with this, I would like to thank you for your attention and hope you enjoy the next class.